strength training and endurance training. So hopefully you remember this because you just took an exam on it. Chronic resistance training promotes enhanced muscle activation and fiber hypertrophy and results in the overall maximal contractile force. I'm highlighting this even though I highlighted it a whole bunch last class period. Mtor, so mammalian target of rapamycin complex 1, so Mtor 1. Key mediator. We talked a little bit in detail last time about how it kind of integrates a lot of information and a lot of different signals, whether it be mechanical or IGF, and gives us increased protein synthesis and therefore muscle growth. And we'll just, for the sake of going over things in detail, so we've got insulin growth factor, we've got our IGF-1 receptor, so it's a tyrosine kinase type. We get our IRS docking protein, PI3K, so our PI3K kinase gives us activation of AKT. That activated AKT inhibits this TSC1, TSC2 complex, which allows the Reb molecule to activate Mtor, which then through 4E-BP1 and initiating factor 4E gives us initiation. Same thing if we're talking about leucine, so we mentioned that was another potential way in which we could stimulate, especially if you were in a nutritional deficient state. You could get through leucine, activation of Mtor, and then there's a variety of processes. And we talked about this one in detail. I've got a little bit of research I'll present today that reuses this P70S6K molecule, just a different pathway that gives us initiation. I'm highlighting it here because some of the data, this is the marker that they looked at to kind of see this pathway, if it was active or not active with different types of training regimens. So this is our general pathway with strength exercise. To counter that with endurance exercise, so we know that with endurance exercise training, we're focused within skeletal muscle now. Remember, we're not talking cardiac at this point. Mitochondrial density, oxidative capacity, all of those are kind of the major things that we're trying to achieve with endurance training within skeletal muscle fibers. And we know that this is primarily done through two methods, through AMPK, so I've just written it all out here. We know it as AMPK, and the calcium calmodulin dependent kinase cascades that all work through activating PGC1 alpha. So we sense states in the AMP to ATP ratio. So we see a lot of AMP, that activates AMPK, which activates PGC1 alpha and gives us through that things like mitochondrial density improvements and improvements in oxidative capacity. So we talked about those independently, but as you can probably, just through your own experiences, recognize that very rarely, whether it's in a rehabilitative state, so you're talking about rehab of an older individual prior or post-surgery, we're talking about just general maintenance of health, whether we're talking about athletes, very rarely are we doing just one of those. And in some cases, you need one over the other, but generally you're trying to do both. So what we've talked about to date is very isolated instances or types of training. And, you would get that if you're talking about the physiques associated with those who would be, like here, a super heavyweight lifter. This is their only job is to lift this weight. Compare that to Tour de France cyclists, very different body types. And as you can recognize, the physiology, the physiological outcomes, the performance outcomes are going to be dramatically different between those two. But what happens if we start to mesh them together? And this really, there's a great story that kind of talks about how this really entire lecture and field of science started out. It started with anecdotal evidence, and this is why it's important to ask questions, and if you don't know the answer, to seek things out. So Dr. Robert Hickson, he was a power lifter. He was in graduate school. I believe he was doing his postdoc. So he just graduated his PhD. He's doing his postdoc, which is consistent with what we do in science. He's doing his postdoc under John Halsey. And John was an avid endurance guy, so what they do usually over the lunch hour is the entire lab would go for a noontime run. Well, Hickson, up to that point, was just doing strength exercise, really didn't care about running, but said, okay, I'll do it. I'm part of the lab, not a big deal. So he would start going on these noontime runs and noticed that all of a sudden he could not maintain his muscle mass, that there were challenges there. He didn't change his regular lifting routine, but all of a sudden he couldn't hold on to that muscle mass. John Halsey said, figure it out. We don't know why this might be happening. Do some experiments. And that's what we're going to start with, is some of Dr. Hickson's original work and then what we've kind of learned from there. So this type of environment that we're really dealing with here is generally referred to as concurrent training. It's the simultaneous integration of resistance endurance exercise with some periodized training regimen. So most athletes are this way. Most people do this as part of their general maintenance of health training programs. We all do it in some fashion or another. So Hickson, because of this anecdotal kind of experience of his own, designed a study. So he systematically analyzed adaptational outcomes. And this is important because this is a problem I have with a lot of molecular studies, is they don't take it all the way and look at adaptational outcomes. Halsey initially did, and that's what makes kind of his initial work so strong. So I'll come highlight this stuff here in a minute, but I like the figures, so we're going to do it. So this is strength, and he had three groups of individuals: those who only did strength exercise, those who only did endurance exercise, and those who did a combination of the both. And we can see here in our strength group, over a period of 10 weeks, nice other than my inability to draw a straight line, this nice increase in strength, just as we'd expect. The endurance group, he's got a point here and a point at the end, because he didn't do his endurance exercise strength training testing throughout, because just that testing would have resulted in some adaptation. So he just did a pre and post and noticed virtually no changes in strength in those who did just endurance exercise. But when it comes to those who did both, they initially saw nice increases in parallel to the strength-only group, lower, but started to go up and then definitely plateaued off when it comes to strength. So this really kind of highlights that, okay, there may be some interaction going on between strength and endurance exercise. These guys did the same strength workout as these guys, but didn't see the same benefits. So overall resulted in a reduced capacity to develop strength, but no compromised increase in VO2 max in this combined group. So there's no figure for it here. But those who did strength and endurance saw the same increases in VO2 max as those who just did endurance exercise. But they didn't see the strength benefits. So this is a straight quote from original papers. We determined how individuals adapt to combination strength and endurance training as compared to adaptations produced by either strength or endurance separately. We found that simultaneous training for strength and endurance resulted in a reduced capacity to develop strength, but did not affect the magnitude to increase maximal aerobic capacity. This was some of the first evidence to highlight that if you're doing this concurrent training, you're going to improve aerobic exercise capacity, but your strength adaptations may be severely dampened. And that's really led to this training adaptation continuum. And this is how we've approached class thus far. Now on the left, we've got the endurance exercise, where we talk about AMPK, PGC1, and improvements in mitochondrial biogenesis. On the strength, we've got AKT, Mtor, there's that P76K, the 4BP would also fit in there, and we see muscle hypertrophy. So you might have the extremes, but most people are in the middle. So what balances out to actually changing? And it appears that if you're doing both, mitochondrial biogenesis side, the endurance side may win out. Additional work has kind of confirmed this. Concurrent training relative to resistance training only, you tend to have a compromised strength, compromised hypertrophy, and compromised power development. Conversely, no impact on endurance performance and VO2 max. So this subsequent work supports Dr. Hickson's initial findings. There's something about the combination that is impairing the strength adaptations. There's two theories, and these are still highly debated today. So two theories. First is that, well, the endurance exercise interferes with the quality of resistance exercise. So we're talking about if you go and you run for a couple hours and then you go to the weight room and try and lift, the quality, the amount of work that you do may just be less because, you've got residual fatigue, you may have some substrate depletion. All of those things could come into play. And that's a little bit hard to quantify. In a lot of early studies, that's one of the things that they're kind of really hit on is, well, did you control for the quality of the resistance exercise? So that's where some follow-up studies and a lot of animal-related research, muscle biopsy studies, is really led to the second theory that we get a compromise of the acute molecular responses activated by resistance exercise that mediate fiber hypertrophy. So there's something happening within the cell, that there's some interaction there. It's not just that they're tired and they're not doing the work. There actually be some cellular things taking place. So these are the two main theories. I'm going to talk about some of the research that drives primarily point B and some of the challenges when it comes to interpreting the data that is out there and whether you fit into theory A or theory B. So we'll start with some of the initial studies that really describe the molecular basis for this interference effect. So it all comes down to AMPK. Evidence suggests that AMP activation significantly inhibits Mtor1. So if you inhibit Mtor, you're not going to see the responses, and therefore you're not going to get the skeletal muscle hypertrophy or the increased muscle protein synthesis. So AMPK activation, significant inhibitory effect on Mtor1. One of the coolest studies that initially looked at this is they took just rats, and they gave them this AICAR, which basically promotes AMP, so adenosine monophosphate. And there's two different subunits for AMPK1. There's alpha-1 and alpha-2, and this is AMPK activity. In the control rats that were just given a little saline, and those that were given this drug that's supposed to stimulate AMPK activity. And we notice in these alpha-2 rats, we see this nice big increase in AMPK activity. So that tells us that the drug did what it's supposed to do, increase AMPK activity. They then looked at, I don't like these graphs and the way they've labeled them, but these are specific proteins on, this is AKT, and this is Mtor. In the AICAR rats that had this increased level of AMPK1 or AMPK alpha-2, they see less activation of AKT and less activation of Mtor. As a result, we look at muscle protein synthesis, significantly decreased. There's no training involved in this here. They simply activated AMPK, and as a result, we're able to decrease muscle protein synthesis through this AKT-mTOR pathway inhibition. You don't need to know these figures. I'm not going to test you on them. It just reinforces this statement here, that AMP activation inhibits mTOR and its downstream signaling, and therefore inhibits muscle protein synthesis. If we look at it a little bit, more detail, we can see that AMPK phosphorylation, which would occur with endurance exercise, negatively correlates with muscle hypertrophy and is associated with attenuated hypertrophy in rodent functional overload models. So if we look at this as plantaris hypertrophy, as a function of AMPK, phosphorylation, more phosphorylation. So down here would be, during endurance type exercise, you would get AMP activation. Down here would be very low, so no endurance exercise. And we start seeing this correlation. More AMPK activation, less hypertrophy. So there's definitely something going on in this interaction between AMPK and Mtor. And that appears to be happening right around the AKT TSC1, steps of our hypertrophy pathway. So this is normal exercise. We just talked about this last class period. AKT inactivates TSC1 and TSC2. So it removes the bully from the playground and allows Reb to have that GTP. So it's promoting this. So AKT inhibits TSC1, allows Reb to activate Mtor, and gives us our pathway to continue. Activation of AMPK1 results in direct phosphorylation of this TSC2. So it's allowing this TSC1, TSC2 complex to be the bully to inhibit Reb, and therefore the signal doesn't continue. It overrides what's happening through this AKT pathway. So up here, AKT, you can cross through this TSC1, TSC2. It removes it. It removes its activity and allows Reb to interact with Mtor. With AMPK, which would come with endurance type exercise, it activates TSC1 and TSC2. It phosphorylates it. It allows it to prevent Reb. It keeps Reb over here in this GDP state so that it blocks this pathway. Well, if we can't activate Mtor, we're not going to activate these downstream regulators of protein translation, and therefore we're going to get prevention of protein synthesis. And this is kind of the best evidence we have to date, the best pathway we have to date, describing this interaction between endurance and resistance exercise. You've got more AMPK coming from endurance exercise. It's going to prevent this pathway, despite it being turned on or trying to be turned on with resistance exercise. AMPK is going to come in and prevent this pathway from continuing. There's some other things that are going on. I'll just highlight it. Do I want to highlight this? Yeah, I'll highlight it. So we've got endurance type exercise. We've talked about AMPK. It's going to, this is what we just talked about here. So AMPK, TSC2, and blocks this pathway. So we get decreased initiation. Calcium calmodulin-dependent kinases, we mentioned that that's a primary pathway that gets activated with endurance exercise. Remember that from previous to spring break. That normally activates this pathway here and therefore reduces elongation. So AMPK and this calcium calmodulin-dependent kinase pathway activates this EF2K, which inactivates EF2 and prevents elongation. I'm highlighting this. put next to it, not a test question. And if I ask it, you can throw something at me if I forget. But I'm not going to ask you about this pathway, but I just want you to recognize that there's multiple pathways in which we can mess with elongation initiation that would normally happen with endurance or strength type exercise. Something that is going to be on there is we talked about the balance, that the amount of protein that's there for structural adaptations, for functional adaptations, is this balance between protein synthesis and protein degradation. I'll let you write these things down, and we'll talk about how this may involve some protein degradation. So not only does AMPK prevent the synthesis of new protein by inhibiting mTOR, it may also promote protein degradation through the ubiquitin proteasome and autophagy lysosome systems. Again, this is why we had to talk about this at the beginning of the semester. So we got these, if you remember back to early module 1, we talked about these two pathways, and we'll focus primarily on the ubiquitin proteasome pathway. So AMPK is going to fire up these systems. So we've got endurance exercise, activates AMPK. That's going to promote this forkhead boxo or FOXO dependent transcription of skeletal muscle specific ubiquitin ligases, example MRF1. So hopefully you remember back this figure we had in one of the earlier lectures. We talked about this, we had to have these 3 different molecules come together. They bound to whatever our protein is that we want to degrade, and then the proteasome, breaks it down to individual amino acids. This is the MRF1. So it's endurance exercise increases MAP kinase, activates FOXO, increases the production of this MRF1, and as well as others. So if you've got more of these, they're more likely to bind to protein and give us, this degradation of the protein. So we get increased rates of protein breakdown simply through endurance exercise. So not only are we maybe inhibiting our ability to add muscle mass, we may be very likely degrading the muscle mass that's already there in some cases. Again, going back to Dr. Hickson, he maintained the same level of resistance type exercise. He now added endurance, but he wasn't able to maintain the muscle mass. He was actually going down and seeing some atrophy, and it could be through some of this protein degradation pathways. There's also this ULK1, and I'll talk about that here a little bit at the bottom. There's not a lot of great evidence for it, but I do want to bring it up because it comes up in the literature quite a bit. So this ULK1, it's uncoordinated 51-like kinase. It's important in the autophagy. AMPK promotes its activity, leading to induction of protein degradation. So there's not a lot of great exercise-related literature to promote this particular pathway. But if we look at some of the fasting literature out there, we can gain some insight. So if you've got, a high glucose state versus a low glucose state, here in our high glucose state, we're gonna keep AMPK inactive, and therefore everything stays like it should. But if you take someone and you put them in a low blood glucose state, and you keep them there, so this will be if you're doing some extreme endurance type exercise, low glucose state is going to help activate AMPK. That's going to inhibit the Mtor, so we've talked about this step already. But here's this ULK1, active AMPK, activates ULK1, and promotes autophagy induction, therefore destruction of proteins. So while we can take information from other areas like an extreme fasted state and start seeing, well, what might be happening during prolonged endurance exercise. Okay, so a lot of this comes from animal work. Obviously, people don't like giving up muscle biopsies, and people really don't like being involved in training studies. If anybody's ever done one, it's about the worst thing you can do in your life. And that's speaking from experience. So a lot of this comes from animal-related work, but there has been some done in human skeletal muscle during exercise. So let's take a look at some of these. You don't need to know anything from these tables, but I want to bring up a few things, and then I'm going to come back to them at the very end after we talk about some specifics. So there's, our study, the sample size, relatively small, training status coming in, the study design, and the exercise protocol. So what did they do for endurance exercise? What did they do for resistance exercise? So 60% of work rate peak for endurance. That's pretty moderate intensity. And unilateral leg press, leg extension. But we see down here, concurrent exercise does not suppress post-resistance exercise protein synthesis rate. Okay, so that's kind of interesting. And if we look through here, 70%, 80% 1RM for resistance, we can see this one does not promote optimal accurate signaling associated with mode of exercise. This Coffey et al. Study where they did sprint exercise, now they're starting to see, some diminished anabolic responses to resistance exercise. Well, this is 10 6-second maximal exercise relative, and they saw an impairment, whereas these were 60 and 70%. And these people were already regularly training. This is pretty moderate exercise. This would be what maybe you'd be doing in a rehab setting. This may be what you're doing in an athletic setting. And we start seeing just anecdotally, well, this one saw impairment and this one didn't. Maybe there's some things about the way they're training, the actual design of the studies that is causing some of this to take place. And if we scroll through some of these, you'll see some of that coming up again. I'm not going to talk about each of these. So there's some contradictory evidence. No conclusive statements can really be made about what's happening, but we can look at the data and we can start to apply it to what we do know. So that's where I'm going to start with role of concurrent training variables. Because this may, and in my opinion, largely explains why some studies see no concurrent effect, there's no limitation, and some do. And again, it all boils down to, what's the quality of the resistance exercise, and did it alter protein synthesis? So our first variable, within session exercise order. If any of you have ever done any considerable training or coaching or whatever, what is the order? Go to the rec, do you do your resistance exercise first, or do you do your strength exercise first? Doesn't matter. If you actually look at some of the molecular data, it would tell you that yes, the order does in some ways matter. So we'll look at kind of some of the challenges and some of the data that goes along with these. So let's start with prior endurance exercise training bouts could compromise performance during subsequent resistance exercise due to substrate depletion or residual fatigue. So in this case, you may be reducing the quality of your resistance exercise. And this is the molecular things that would happen. You do your endurance first, AMPK, PGC1, mitochondrial biogenesis. You then go to the weight room and you would, do your resistance exercise. Well, because you're tired, you just ran for an hour, your exercise quality may be down, therefore there's less stimulus, and therefore you're not going to activate AKT or mTOR, and therefore going to get some decreased translation. So this would say, maybe you should reverse this order, but that may not fix the problem. If we look at the actual metabolic signals, so signals from endurance exercise that would inhibit protein synthesis, so AMPK, are relatively transient, only around for about 3 hours, compared with the anabolic responses that are there with mTOR1 that can be elevated for up to 24 hours. So performing resistance exercise first allows AMP activation to impede the anabolic signals. So, if we remove these, and we activate AKT, mTOR, and get our translation, then we do AMPK, this gets activated and then it feeds back and blocks this. So let's look at some actual evidence of these two types of training protocols. And this goes back to the Coffey et al. Study, which I really like because, again, it's high-intensity exercise where we would get this AMPK activation. And then they did, a resistance exercise that consisted of leg extension, 80% 1RM. The same muscles were going to be activated during resistance as it was in the sprint exercise. So they just look at the study design, sample biopsy, and then they were split. You either did resistance exercise, 15-minute recovery, which seems appropriate. That's about what you would do if you were at the gym. Followed it by sprint. Here's sprint in the second group, 15-minute recovery, and then resistance exercise. And then they took biopsies throughout. And they concluded that performing repeated sprint exercise in close proximity to resistance exercise attenuated anabolic signaling and increased catabolic activity. And how did they come up with this? So if we remember back, we have our growth factors. Here's our PI3 kinase, AKT, mTOR pathway. And through mTOR, we learned about this. I also mentioned just today this S6K, increasing translation, promoting cell cycle progression. So if we look at the phosphorylation of this S6K, we'd like this to go up with resistance exercise. So in the group that did resistance exercise first, followed by sprint. So they did their first exercise, which was the resistance, goes up, as we would expect it to go up. Those who did the sprinting first, no change. We wouldn't expect it to go up. They didn't do that type of exercise. Then when we do in this open circle group, they took 15 minutes and then they did sprint. Notice, came back down. The sprint group, it was down after their first exercise, and even though they did a bout of resistance exercise, it never went up. So in this case, performing sprint exercise prior to resistance exercise completely removed the anabolic signal. The signal never got down here to increase this translation. Yeah?
If you had someone do this resistance exercise and then just completely stop exercising,
how long would it stay elevated?
Yeah.
That's a great question. So if you they didn't do that, and that's a major limitation to this study, is they should have had a third group that just did a bout of resistance exercise and that did nothing to see if it would stay elevated. Their justification was prior literature showed that it does stay elevated for up to 12 hours. So they kind of leveraged other studies. You can kind of get it. They're taking biopsies from people. IRB likes you to minimize pain on people. It's still a limitation. But if on the current, based off of previous literature, you would expect it to continue to be up. So to that point, I'm going to take a lot of stock in this response. here. But what this does tell you is that if you do the resistance exercise, it should go up. This group, when they did the same amount of resistance exercise, but just did it after sprint exercise, there was no change. So it really highlights that the sprint exercise prevented the signaling associated with muscle hypertrophy that had been caused by the resistance exercise. So there is definitely some order effect. You do the aerobic and then you do the resistance, you may not get the same signaling with that resistance exercise. I'm going to highlight this bottom point here. Results suggest that repeated sprint activities are isolated from resistance exercise and that adequate recovery time is going to be needed and should be considered within periodized training such that incorporate these divergent exercise modes. So the order and the time in between them are very likely going to matter. Questions about, what we're talking here with ordering. Okay, so that data suggests that we might need to consider recovery time. Severely under-researched. We know very little. All we know is that transient activation of the proteins by endurance exercise that inhibit protein synthesis, so things like Ampk, and mediate protein degradation like MRF1, so this is our ubiquitin, suggests that commencing resistance exercise in close proximity to endurance may further compromise the anabolic response to resistance exercise. That's really all we can say at this point. We don't have the research to say 15 minutes or 30 minutes or 2 hours. Longer the better, to what it appears. So that's recovery mode. What about training intensity? And I think this, personally based off of looking at the literature, this may be one of the biggest drivers. So we know that higher intensity endurance exercise, we're going to get a greater metabolic perturbation. So acute molecular interference when compared to lower endurance exercise may come into play. So this is phosphorylation of Ampk. Remember, that's the thing that should be inhibiting Mtor. Cool little study here. They did 30 minutes of exercise. And they had two groups, a constant load group. So they did 35 watts, which for this group was pretty decent intensity. I think they were older individuals. So 35 watts, and over this 30 minutes of exercise and 60 minutes post-exercise, really no change compared to rest. So if they did low intensity exercise, really no Ampk increases. Then they had a group do incremental. So every few minutes it went up. 35 watts, no change. So about 10 minutes they were 35 watts. They went to 65 watts. It goes up, but really nothing too exciting. 85 watts. Once they got to 85 watts, we're talking about a 2 to 2.5 fold increase in Ampk activity. So this problem of interference may only come into play if you're doing high intensity exercise. Remember, the coffee study was sprint. They were high intensity maximal sprints. This is what you'd expect. If you're talking about doing 50% VO2 max for 30 minutes, you're down here. Probably not a problem. So the negative regulators of protein synthesis, such as AMPK and 4-BP1, is increased by endurance exercise in an intensity-dependent manner. May also come into fiber types. Well, if you're doing high-intensity exercise, you're recruiting the same type of muscle fibers that you would be recruiting doing strength-type exercise. Remember, we talked about these molecular pathways associated with resistance exercise occurring in the type 2 fibers. Well, you're recruiting those during this type of exercise here. And we're also going to see the glycogen depletion and more AMPK. So those things could come into play. So we talked about this study already, where we have the order effect. trying to look at my notes here. Yeah, so this is a study where they did just resistance exercise. So they did resistance exercise and then rested. And this is phosphorylation of this S6K1. So remember, that's something that's going to be turned on by Mtor. Rest. So in our resistance only group here, rest 1 hour post, it's elevated. 3 hours post, still elevated. If we did resistance exercise followed by cycling exercise, 1 hour post, significantly decreased. 3 hours post, still significantly decreased. It goes up in this study. So there is some activation with the resistance exercise, but it's severely dampened because of the order. Did resistance followed by cycling, only 15 minutes in between. So there's clearly some things going on here when we're talking about the order and the interaction between these types of exercise. If you go back and look at that big table and pick out the ones that saw no effect, you're going to see a couple things. Really low intensity exercise, and the volume of exercise is going to be considerably lower. And the last thing is training volume. Some people are doing these types of exercises every single day, and some are doing it a couple days here and there. Who's at risk for some of this interaction? So role for volume-dependent interference supported by studies showing no interference when the training for endurance is less than 2 sessions per week. But if you start increasing the training volume, now you start seeing some attenuated maximal strength gains. We start getting where greater attenuation of strength and hypertrophy as we get greater frequencies of endurance exercise, so we get above that 2 to 3 days per week. But we really don't know what's the magic number. Remains to be determined whether total weekly endurance training or training frequency, which is the more critical factor. We don't really know. So conceptual framework for the potential role of individual concurrent training variables. So there's some interference effect going on. There could be some compromising of the stimulus. So they're just tired, so they're not doing as much work and therefore not adapting. Or it could be some attenuation of the anabolic signal, through AMPK. And I like this little figure. So we talk about, when we start talking about combining these two, we do, the order, the proximity, the intensity, the volume, especially these three here, we start increasing those. We start having potential for residual fatigue, potential substrate depletion. We definitely, when what we've talked about primarily today, decreased anabolic response to resistance exercise, in the end, giving us decreases in fiber hypertrophy, and therefore the overall improved performance. So clearly there's a lot of things that we know and a lot of things we don't know. My takeaway is that this really becomes a problem if you're dealing with athletes. If you're talking about someone who's training every day, you're trying to get maximal gains, they're going to be doing high intensity aerobic exercise that would be like sprint training where you'd be getting that AMPK activation. This likely is going to be a problem. If you're talking about the average day-to-day person who's just recreationally active, not really concerned, if you're talking about the rehab patient, we're talking low intensity aerobic exercise. They're not likely going to be doing sprints, and therefore this may not be a problem. If you do have concerns, space it out. Do one in the morning, one in the evening. Again, if we can get that duration between the exercises, that seems to really promote things a little bit. Questions? Okay, that's all there is for today. See you on Tuesday.